There's a lot of work going on these days around container standards, which can make things kind of confusing. The goal of this presentation is to help clarify how they all fit together and how they are working. All right, first I want to start with some background. What is a container? On the left, we have a traditional operating system, and you'll notice a couple different instances running as virtual machines running on a hypervisor. You'll see that there's an application, its dependencies, the kernel, all are running inside of a single virtual machine, right? And that's kind of a complete operating system. That's what instances look like today in virtualized environments. On the right, I want to compare, what a containerized environment looks like. Instead of bundling the kernel and the OS dependencies and the application all together, we just bundle the application and OS dependencies together. And that's the unit that we move around when we deliver applications. To dig into this a little bit deeper, I want to show kind of, what containers are. So I always say that they're basically fancy files and fancy processes. In this particular part, we're showing, a traditional operating system like Red Hat Enterprise Linux. You would have Bash, and there would be an RPM package that delivers Bash. And when you install that RPM, it would pull in all the dependencies, libtinfo, libc, other libraries and dependencies. On a traditional operating system, that just gets installed, in the operating system, and essentially the application becomes part of the operating system. It's just kind of in the same file system and just lives there. In a containerized world, when you're building the container image, you pull the RPMs in, it pulls in its dependencies, and then when you're done getting that container image looking the way you want, so you install all of your apps and maybe you put your own code on there and your own scripts and things, you save that container image. And then that container image is held separate from the underlying container host, which can be a traditional Linux system. But you'll see that the application, all of its dependencies and everything are bundled statically in that container image. And so now you can move that container image around as the unit, as opposed to just RPMs or full virtual machines. So it's this kind of, it's a nice grouping of applications and their dependencies that make containers really convenient. But when they're running, I call them fancy processes. If you look at what a normal Linux process looks like, it's essentially a data structure that gets created in the Linux kernel, and then that the kernel allocates resources to it. Containerized process is the exact same thing. The only difference is in a Red Hat world, this is created with a different system call. So when processes are fired up, it's created with a clone system call as opposed to a fork or an exec. And also we create SE Linux context for it. We create C groups for it and seccomp, to protect different system calls from accessing the kernel in certain ways. And so if you really think about it, a containerized process really isn't that different than a regular process. It, in fact, is just a fancy process. So in this section, I want to highlight how standards are enabling containers. So up to a certain point, software containers are very similar to shipping containers. If you look at, this picture, we have a bunch of bags, barrels, box, crates. They're all different form factors. It can be hard to stack them and use tooling to move them around. For example, you couldn't use a forklift, because none of them are really set up to do that. You'd have to stack them on a pallet. The idea of a shipping container is to kind of standardize that format. And so you can put a bunch of bags, barrels, boxes, and crates, which are very similar to packages like RPMs, inside of that container and then ship it around. So in the software world, it's the same thing. You put a bunch of RPMs into a standard software container image, and now you can move that software container image around. And the beauty of having a standard is, once you standardize that, you can protect your investment. So if you create 1,000 container images and they meet a certain format standard, they're good for a long time. You don't have to worry about, I built them in September, now they're broken in November, and we have to rebuild all 1,000 containers with new tools that enable some new version of a container format. So this kind of, in the way that you learned it, might be different now. And so the idea of having a standard is you can invest in tools, you can invest in your learning. So time, effort, money, you can kind of leverage that over an amount of time to get some kind of return on investment. Another advantage of container standards is that it enables an ecosystem of products. And products allow for investment. So a healthy ecosystem is really composed of, vendors that are making money, investing in engineering, helping customers with a business problem, which then creates more money, which then allows more investment. So that's a healthy cycle of product cycle, and we want that to happen. And container standards help enable that. And thirdly, the community. If you think about the way open source communities work, a lot of it's based on individual contributors, and individual contributors want to contribute to something that is meaningful and that has that basically provides value for some amount of time. Again, they want if I contribute to a certain project, I'm hoping that people will use that project and it'll be useful for an amount of time to where it has some name recognition and helps people for a long time. So standards help enable that. If I build a tool that builds container images and it gets a big following, I want that tool to be leverageable for years, probably. I'd like people to be able to use it for a long time. All right, in this section, I'm going to dig into the different standards and how they all fit together. So first, let's give a quick overview of a lot of the different standards that are out there. And so if you've paid attention to what's going on in the container ecosystem, there's a lot of different standards. Some compete, some work together. But these are kind of 5 of the biggest ones that are out there. And some are industry standards that are managed by third-party organizations, not a single vendor. Others are de facto standards. Other are kind of single vendor standards. So if you look on the left, Open Containers Initiative. So this is managed by the Linux Foundation, and it is an open standard that is participated in by many different vendors, and it governs 2 very important things. So the image specification, what a container looks like when it's saved on disk, and the runtime specification, how to turn it into the fancy process that I mentioned before. The one in the middle is part of the Kubernetes community. It's Container Runtime Interface. It's a standard that was created to allow you to swap out a container engine. So, for example, Kubernetes can use Docker or Rocket or Cryo or any other container engine that has a runtime interface standard or has a shim that can essentially serve as a driver for the container runtime interface standard. So that's sort of a de facto standard. And then on the right, we have 2 standards that have formed around networking. And the container network interface is the one that Kubernetes uses. We call it CNI. It's also the one that was used by CoreOS, and I'll kind of talk about this a little bit around Rocket. And then there's a competing standard called CNM, which is kind of a Docker-only standard. Both these standards are still out there. They're kind of competing, but the good part is there's only 2 of them that are really kind of in the lead. And so at least network vendors are kind of investing in both of them. So you'll see a lot of the big network vendors kind of have software and hardware that work with both of these standards. So this is good, even though they're still competing. So now I want to dig in a little bit deeper into how all of these standards play together. So I tried to set up kind of what a basic container environment looks like. In the center, you have a container engine. A container engine is kind of the thing that handles API calls. And, for example, with Docker, you have a Docker daemon, and it's the container engine that runs on a container host, which is the thing at the bottom. And when you run, for example, the command docker run, you're running a little command line interface, program that basically goes and talks over an API to the container engine, to the Docker engine, and then pulls down a container image, which is at the top, from a container registry, which is also at the top, expands it onto disk, into a file system, and then ask the kernel, hey, kernel, please go run this process for me in a fancy way. And then, so that's kind of the experience that changed the world, right? The container image registry engine and host, that kind of stack of software is what kind of changed the world about 4.5 years ago. Being able to run containers with a single command and it just goes and pulls the image down, it all just works. That was really cool. Then in the last couple of years, container orchestration has taken off. And the idea of container orchestration is that it's able to manage those container engines across many hosts. So maybe you have thousands of containers or thousands of hosts or both. And the container orchestrator kind of handles, I always joke, it handles if you have 2 hosts or 2 containers. So, it helps if you have 2 Apache containers that both need the exact same port. It also helps if you have 2 hosts and you need to schedule, containers to different hosts. And so all of those working together is kind of what a modern containerized environment looks like. And then we'll move to the colored boxes. So you'll see that each of these standards, basically govern the interactions between some of these things. So the container image specification essentially governs, how a container engine goes out, pulls down an image, and what that format looks like, what that data and metadata in that container image looks like. And then the runtime specification essentially kind of governs the relationship between the container engine and the container host. So run C is a very common, is the reference implementation for OCI, for the OCI runtime specification, and also a very common one. There are other OCI compliant or other runtimes that target the OCI specification. But run C is a very common one. It's the one that's used by Cryo. It's used by Docker. It's used by a lot of other people or a lot of other projects. But again, run C kind of talks to Linux kernel on the host and then tells it how to fire up the containers. Then, I mentioned the container runtime interface is a de facto standard that is in the Kubernetes community that allows Kubernetes, think of Kubernetes as the container orchestrator there, Kubernetes and OpenShift, which OpenShift is Kubernetes, basically. You can swap out the container engine. So you could use Docker, or you could use Rocket, or you could use Cryo, which is what I will demo later. But basically, it's nice because you'll notice that the container engine is boxed in by a bunch of standards, so we can swap the container engines out. And we can swap the orchestrator in and out, and we could swap hosts in and out, and we can swap, different registries in and out. And so the nice part is we can swap out best of breed tools in any of these places. And that's really, all these container specifications working together really help kind of provide that ability. And then one last one I want to talk on, I won't talk a lot more on, but it's CNI and CNM. You'll see that there are networking interface standards, and the one on the right kind of really interacts with a Docker engine, and so it's kind of a single vendor one. It also works with Swarm. CNI works with Kubernetes, so it can work with kind of orchestrators, or it can work with Rocket, which is another alternative engine. And you'll see that I kind of have dotted lines connecting both, just so you can kind of understand the interaction there. And what that does is it kind of governs the interface between the container engine and the host from a networking perspective. And so let's dig into the OCI specification. It's pretty similar to what governs real shipping containers. The analogy, in fact, is strikingly good. So people don't realize, but it seems like it's something very simple, right? A metal box. It's a 20-foot metal box, should be really easy, but it's not. So there are many, many ISO standards that govern shipping containers, what they call, standard shipping containers. So in this example, I kind of showed just a few of them, but there's many, many more. But like ISO 668 determines external dimensions, 1161 determines hook dimensions and basic strengths. 1496 governs the weight rating that any container is tested at. And you'll see, just for something so simple like a metal box, the same is true with software containers. So Linux and Windows, containers or images are essentially very similar to this. The OCI image specification governs this, and it's good because it can, prevent a lot of problems. So things like catastrophic failures. In a port, a catastrophic failure looks like, cranes dropping containers and possibly people getting hurt or dying or losing cargo. And you can imagine Shanghai port with thousands and thousands of shipping containers, maybe hundreds of thousands or million shipping containers. You can't have failures in your automation, right? Because if a container gets jammed up and breaks a crane or clogs up the pipeline, you can't move containers on and off ships. Well, the same's true when you get into automation with software. So if the container image breaks and one piece of your tooling updates and then it doesn't work with it, you can imagine catastrophic failure in things like your CI/CD system, where you're building thousands of applications and rebuilding containers all the time. You can have catastrophic failures in automation when standards like this break. And I mentioned before, but it's so simple, but yet it offers such immense interoperability, right? Like having a standard on the way these files and metadata work together, which is basically what a container image is. It just provides so much more peace of mind that software is going to work together. And finally, I mentioned it before, but it protects your investment, right? So in the physical world, you would, you want to be able to buy cranes from one vendor and ships from another. You don't want to have to buy all your ships, trucks, cranes, trains, all of your loading and unloading equipment and all of your transportation equipment from one vendor, right? You want to be able to buy from the best vendor at the time, and some vendors go out of business, you don't care, whatever. But you can buy, different cranes and different, forklifts, for example. The same is true with software, right? You want to be able to swap out registry servers or orchestrators or container engines or hosts or whatever you want, but you still want to be able to govern, that you can have all of your container images live in a single container registry, like an enterprise container registry that may have thousands and thousands of containers in it. And so it really helps protect your investment in both your learning and your financial investment in buying software or building out, an environment, et cetera. So in this section, I want to dig a little bit deeper into the OCI runtime and image specification. You'll see from this drawing, moving left to right, that this is the basic workflow of how a container is started and then ran. And going left here, this is the image specification that I mentioned, specifies how the metadata in the manifest is laid out on, in a file, and how the image layers are formatted and connected together. The container engine's job is then to take that standard set of data and that image manifest and generate a config.json itself, which is a very standard formatted file that is part of the OCI runtime specification. And its job is also to expand those image layers into a root file system. And a root file system is really nothing more than a directory structure that looks very similar to Unix root. So if you were in root, it would be /user and /bin and sbin and all of the things that you're used to seeing in a Linux or Unix file system. And then the container engine, hands that off then to any runtime compliant or OCI runtime compliant piece of software. runc is the reference implementation, but there are actually others like Railcar and runv. There's a specially modified version for, I think, of runc for clear containers. And there's a lot of innovation going on here in this space kind of to generate new OCI compliant runtimes because some people want to do different things. The most common one is runc. It's what's used by Docker. It's what's used by Cryo. It's a very common one. It has a lot of features for things like setconf and all kinds of things that you would want to pass to the clone syscall for different namespaces. And it's really good at talking to the Linux kernel because it has a lot of capabilities. And then finally, the kernel on the right, you'll see the clone system call. If you're familiar with kind of the Unix 101 internals, these system calls are how a process creates another process. And the most common ones were fork and exec, and that's how Apache and Bash and all these other things that create other processes work. But the concept of containers requires what we call a clone syscall, and the clone syscall is what actually creates a namespace. And a namespace, think of a namespace as an illusion. The child process only sees the file system that was mounted in that namespace. It only sees the process IDs that were created in that namespace. And so that's what gives you the illusion of when you're inside of a container and you ls and you see a fake directory system that looks like a real Unix system, or you see a set of processes. You only see one or two processes running instead of all the processes on the system. These are called Linux namespaces. And so the kernel is what governs how all this works, and the clone system call is what creates that process with that sort of set of illusions that make it look like it's running in its own VM. So now let's go even a layer deeper. Start in the middle, and the most common role in this whole container space is the user. That's the person or even an orchestration system that wants to talk to a container engine to tell it to do something, to fire up a container, stop a container, pause a container, whatever. The user is really in control of overriding anything that's set by default by the builder or the daemon itself. And so, for example, it's really common for a builder to specify an entry point or a command that's ran by default. The daemon could override that. That's a completely possible option. But more commonly, the daemon would add to when it's generating the config.json, would add something like setcomp profiles. And then the user might override those setcomp profiles and say, hey, the default setcomp profiles that this container engine use are good, but I have my very specific ones that are tailored to my application. And so the user would pass a command line option to the runtime, to the container engine and say, hey, start this container, but use this different setcomp profile, or mount this data volume, or use this different CMD, run a different command, or specify some environment variables that are very different. I mentioned maybe earlier that this week I saw a really interesting use of this where the Microsoft SQL Server container actually has a EULA agreement, and it says accept EULA. And the end user, as they're firing up the container, has to put accept EULA equal Y. And so that's essentially a way of them complying with a legal or agreement, to run a container. So this can meet technical things like overriding the seccomp profile, or it can just be business, arbitrary but intentional, environment variables that represent business agreements or things like that. So it's really powerful because, again, it's a contractual way for the builder, the daemon, and the user to all kind of agree on how things are going to get ran. And so the container engine has a lot of responsibility around pulling down those container image layers, the metadata, generating that config.json, adding its own defaults, then allowing the user to override those defaults, and then finally handing that final root file system, which is essentially directory and a config.json. So a single file, single directory, off to run C or to any other OCI compliant runtime, and then again off to the kernel, as I mentioned before. And then the kernel is responsible for making sure the containers keep running. If they die, then the engine or the orchestrator may tell the engine to start another container, et cetera, et cetera. But really, at the end of the day, they're normal processes running in a Linux system. Okay, now I want to do a quick demo. But before I do, I want to get into what I'm going to show you. So what I'm going to do is I'm going to swap out the container engine running underneath an OpenShift instance. And before I do that, I want to tell you why you might want to do this. So Cryo is an alternative container engine that Red Hat is working on very heavily and working in a community with a lot of other participants to try to create an alternative for Kubernetes that is targeted at production container workloads. And the reason why is Cryo is lean, stable, secure, and boring. That's the goal. If you run around in container circles, there's this concept of boring, and it might not sound like something you want, but underneath, a Kubernetes environment like OpenShift, you do want something that doesn't change. And so you want a small footprint, minimal daemon, doesn't break API interfaces with every version, implements every security feature needed by Kubernetes, and yes, boring. That's what we want, right? And then finally, you want something that's open source, that's community-driven open source. You don't want something like Android where it's not exactly community-driven. It's more like, here's the code, have fun. Everybody can look at it, but it's really hard to build anything with it because you can't really contribute back to it. You want something that's easy to contribute to. The community's hungry to take changes and ideas from other people in the community, and really hungry to meet the needs of all the participants in the community, which is something that Kubernetes is, and so is Cryo as part of Kubernetes. That's very much how it's governed, and then follows an open governance model. Just like Kubernetes. You don't want something that's controlled by a single vendor, and so these are all the reasons why we think that Cryo is a really good alternative, container engine. So I'm going to show you using the models that I showed you before with the container standards. This is what a specific implementation looks like. I show on the left here, you have a Docker engine, and basically, there's a manifest, and the Docker engine pulls down the manifest and image layers, decompresses it into a root file system, hands it off, to run C as a config.json and root file system, and then run C talks to the kernel and blah, blah, blah. So on the left or on the right, we're going to move this over to Cryo, and you shouldn't be able to tell the difference because, again, standards govern the images and they govern the runtime specification. So at the end of the day, the exact same images are pulled down into a cache for Cryo to run, and these are from the exact same Red Hat container registry. So we're going to pull them from registry.access.redhat.com. And the cool part is you're running the same container images with two different engines, but then processes get fired up in a very specific way, and they are very compatible. In fact, they're so compatible that Kubernetes doesn't even notice. So one more thing for those that don't understand Kubernetes and OpenShift. OpenShift is essentially this is the kube master is the OpenShift master, and the kubelet is the OpenShift node. And the way OpenShift works is it's really a compiled binary that contains the master and kubelet in it. And so you'll see that the configuration I do is a little bit different, but I kind of want to show all the pieces in the workflow of how it works. So, developer administrator comes in, hits a load balancer, which would then load balance between different OpenShift masters. The OpenShift masters have an etcd, which contains the defined state of how this cluster should look, which container should be running where. And what this Kubernetes master does is these controllers essentially watch the cluster and constantly try to make the actual state match the defined state. And so that's kind of the basics of how this all works. And you could imagine you could have much more than 3 nodes. You could have 1,000 nodes and 3 masters. And on each of the nodes, you would have a Docker daemon, container D, and run C. And this is kind of what a Docker setup looks like. And then they talk to the kernel, and then a bunch of containerized processes gets fired up. And then just for fullness, I showed that, look, a registry, registry with different images can be running inside the cluster and consumed and used within the cluster. And what I'm going to show you is this is what it will look like before, and this is what it will look like afterwards. So it's pretty simple. We go from Docker to cryo. And when you look at the bigger part of the ecosystem, it's not much of a change. And that's exactly what we want. We don't want to interfere. We just want to replace this one piece with something small and boring that works and doesn't break, and is really targeted for Kubernetes use cases. So let me jump over to my terminal. So I am now on an all-in-one installation of OpenShift 3.6 running on RHEL 7.4. And so I want to kind of show you, we have right now an OpenShift master, an OpenShift node, and a Docker daemon and a cryo daemon all running at the same time. But we'll do a Docker PS, and you'll see some things. You'll see containers running. These are running workloads that are required by OpenShift. So you'll see like registry console, the registry itself, and the router. And these are running in Kubernetes right now. So I'll show you from the Kubernetes perspective. You'll see these running as what are called pods. And so these pods, kind of map to what you're seeing running in Docker up here. And so we know that right now, and then I'm going to show you the config file that dictates this. So the node config, you'll see under the kubelet arguments, has nothing special, about it. It's just kind of labeling the nodes, or this node in particular, and saying don't use CRI. But basically, what this does is this automatically uses Docker. But now I'm going to show you we can actually just copy node config -cryo to node config, and then restart the OpenShift node. So you'll see this is just systemd restarting it. And this is a little hack to fix something because you're not supposed to change container engines live on a Kubernetes system, but I'm going to show you that it works. So I have to kill the OpenShift router manually. It's a little bit of a glitch when you change container engines live. But like now, let's do a Docker PS. You'll see these Docker containers are still running, but let's stop Docker so that you know that I'm not lying to you. So now it's going to stop these containers. And so none of them will be running. And then I'm going to show you the magic that OpenShift still has its pods running. OC get pods. So you'll see we still have a router, a registry console, and a registry running inside of OpenShift and our same completed, RHEL 7 one. In fact, let's delete this guy. And then I'll show you a new one running just so you can see. Run. And so this command, OC run, I'm just going to run a RHEL 7 image bash interactive. And you'll see that I am now inside of a container running in cryo, and it looks identical. You really can't tell anything's different. In fact, to prove it, I'm going to show you cryo CTL, CTR list. You'll see that here are containers running in cryo. So we've now replaced Docker with cryo very transparently to the end user. Again, you can't really tell any difference. It just looks like regular pods. So you'll see we replaced the Docker daemon and container D with cryo, and it was very easy. And in fact, we're able to do it live on a system that's running, and it didn't even break the system, which is actually pretty amazing. Kubernetes is not designed to do that, and I don't try that at home. But the fact that it worked without me having to show you 2 different systems was really convenient and nice. And I thought it would kind of show you that we want simple and boring works here. So that's it. Thanks.